Hello, good morning, everyone. I hope everyone is fine this morning. We'll be able to start today's session on topic carryover as a method. So our presenter for today is Mr. Antony Jaccodul, who will take us through the session. And then after the presentation, we'll be able to go through the Q&A. Thank you and welcome.
Hello, good morning. I hope you're able to hear me. So, our session today is on carryover as a method validation characteristic. So, I'm putting my presentation up shortly. I don't know whether you're able to see my presentation.
Yes, your screen is up, so we are waiting for the PPT.
Is it there?
Yes, it's okay.
All right. So, welcome to this webinar series. So, most of the time on method verification, we've always concentrated on three characteristics. That is accuracy, precision, and linearity. But as the world advances and other parts of the world also do carry over as well as a performance characteristic in method verification. So it's an important topic because at times it's a forgotten area, but it impacts test as much as possible as other method verification characteristics. So for our topic today, we'll be able to define what carryover is in the context of method verification. We'll also be able to explain carryover, why carryover is essential in ensuring reliable results in quantitative tests, and also describe the procedure and also do the interpretation and identify requirements, and also recognize how often this should be able to be done. So method verification is something that anybody in the QMS ecosystem has been able to replay, to work with, to go through, and also to be able to implement. So on ISO 15189-2022, method verification is about confirmation of claims by the manufacturer that the test that you are putting into use in your laboratory is fit for purpose and is fit for use. And this can always be exemplified by looking at various characteristics, that is accuracy, precision, linearity, carryover, there's also robustness and ruggedness, and many others. So for the purposes of the webinar today, we're going to concentrate on carryover tests, or what is carryover. Just as the name suggests, leftover, carryover, anything that remains when you have tested one parameter to the other, we normally describe as a carryover. So carryover is the unintended transfer of analyte or sample material from one measurement, usually of high concentration, into the next measurement, typically low concentration, which can lead to falsely elevated results. So when you're having a high concentration sample, let's say you have albumin and the concentration is up there, almost maybe 900 or 500 mg per dl or whatever it is, the units of measurement, you can always have an intended transfer from that high concentration sample. And when you're running the following sample that is low concentrated, those particular unintended transfer can happen, especially when your chemistry or hematology or immunoassay analyzer is not able to prevent or minimize as possible the issues of carryover. And your results can end up being elevated. And this can always be catastrophic, especially in tests that have very minimal advances in terms of values. You can always have just a small tinker in the value that leads to a falsely elevated results and causes them to be a panic result. So things like troponin, things like potassium, things like, just to mention but a few, when you have just a small carryover or a small tinker in the results that come out, you end up having a very panic value if that unintended transfer happens. So this is critical in quality control process to ensure that automated analyzers and lab procedures do not produce false results due to the incomplete removal of previous specimen, reagent, or washing media. So remember, carryover can also be as a result of carrying over washing media to the sample, carrying over leftover results from the previous results into the sample, causing unintended, falsely elevated results or results that are false in the whole process. So it's an important process to ensure that our samples that have very high clinical significance, especially when you carry over unintended transfer of analyte or sample material, they do not cause panic in the laboratory. So why is carryover important? If carryover is detected, it can lead to systematic positive or negative errors, false positive or negatives, and ultimately impact clinical decisions and patient safety. And this can even be impacted heavily also on qualitative tests. When you also have a very highly elevated sample X that was having a high positive, maybe HIV value, and then you carry it over to the next sample that has no infection, it might cause a false positive in the sample that is preceding that, especially if your analyte is not able to have proper washing mechanisms, or they don't have the deproteinization process that do not really fall into place. You might be able to have these particular issues. So carryover is important because it prevents analytical errors. So carryover, if it's not really looked into, it what causes a lot of cross-sample contamination, leading to inaccurate readings and unreliable results. It also ensures patient safety. So erroneous results can lead to misdiagnosis, incorrect treatment, and negative clinical consequences for patients. So when you transfer an intended sample into a patient that was otherwise okay, you'll be able to have that patient misdiagnosed and a correct treatment applied for that particular patient. And therefore, patient safety ends up being compromised. Carryover also is used in verification and validation of automated test systems. It helps confirm that automated analyzers, such as clinical chemistry, immunoassays, or hematology, are functioning correctly and are meeting specified specification as per the manufacturer claims. So it's an important aspect in eliminating analytical errors, ensuring patient safety, and also ensuring that verification of these automated systems are top-notch. Clinical significance of carryover. For some tests, even a small amount of carryover can have significant clinical impact. As I've said earlier, an acceptable carryover for one test might be catastrophic for another with a narrower critical range. For example, there are some that are low impact samples. A 1% carryover for plasma albumin test might be clinically significant. Some of the high impact carryovers, the same 1% carryover for a high sensitive cardiac marker like troponin assay can lead to life-threatening misdiagnosis for patients who do not have a heart damage. So if you have a carryover of 1% from a sample of troponin and the same 1% in albumin, you'll find that it is bad in albumin, yes, but it is catastrophic in samples like troponin. So in such particular scenarios, carryovers should be able to be minimized as much as possible because it can lead to damage of patient organs. And when treatment is applied that is not appropriate for that particular patient, you might even lose the patient in the long run. So it is very important that these particular tests are, especially the high sensitive test, you should be able to do carryover as much as possible, as much as you're doing others. Common types of carryovers. We have sample to sample carryover. This applies when residual analyte from one sample is carried to the next and often lead to often due to inadequate cleaning of maybe pipette probe or many others. So you can have residual sample from a high positive sample and then you carry it over to the next one, maybe due to improper washing. But I know most of the analytes nowadays have very good aspects in terms of washing of the sticks of the needle probes. We can also have reagent carryover, a carryover from previous reagent that was used. Cuvette or vessel carryover, when your cuvettes do not really clean properly, or you are reusing them, or you don't apply new cuvettes and they don't clean properly, unwanted materials is left in the reaction vessel from the previous test, causing erroneous result in the preceding test. So in the PCR at times, amplified DNA from one reaction contaminates subsequent reactions, leading to false positives in molecular tests like PCR and many other tests that we have said. So how do we minimize carryover? Labs normally use different strategies to minimize carryover and maintain accuracy of quantitative tests. One way is the optimal wash cycles. So most machines nowadays, optimization of wash cycles is quite enhanced. So they increases volumes and number of washing steps between samples, particularly after high concentration samples. So instead of having only one washing steps, most machines nowadays increase the testing, the wash volumes of the test of the wash materials, and also the number of steps of washes between one sample to another, ensuring that as much as possible, we do not carry over remnants of the previous samples. We can also have run order optimization. So as you read your reagent inserts, as you read your equipment manual, you need also to concentrate on carryover minimization strategies of various instruments. So look at the optimal wash cycles. What are the wash volumes? What are the wash numbers of tests between one samples to another that really minimizes this? So run order optimization. Organize the testing sequence to analyze low concentration samples before high concentration sample whenever possible. So if you know clearly that the samples that you're having are either maybe from a patient that might be able to have a previous history of the same disease or those kind of aspects, you need to see how those particular samples are run in the laboratory. And that's why whoever is running samples in these particular spaces, whether it is clinical chemistry, whether it's immunoassay, whether it is the hematology, whether it is the cardiology and samples, or even coagulation, you should be able to concentrate also on the patient history. And that's why on ISO 15189 2022 version, I think they are around close. If you look at the process requirements chapter of the particular standard, there's a lot of concentration on ensuring that the data that you correct on your request, lab request, they are complete and having those particular patient histories so that you're able to also read and understand that history, so that when you're running the samples and there's a potential for you to have carryover component in one sample to another, you need to run the samples that are otherwise normal or have low concentrations first before you introduce those other ones whenever possible. Dedicated channels. On some analyzers, dedicated specific probes or reaction vessels to test samples with known high carryover potentials. So some equipments have those particular components. Disposable consumables, use of disposable pipette tips, cuvettes, and other consumables to prevent mechanical transfer of analytes. So most of the equipment nowadays, you normally have their single-use pipette tips, single-use cuvettes, or single-use reaction vessels to ensure that the unintended transfer do not actually happen. Also, regular maintenance, perform routine maintenance, including replacing worn-out seals or tubings to ensure that all fluids are functioning properly. So in your machine, ensure that the fluidics components are functioning properly and there are no leakages as much as possible. So these are just a few of the strategies to ensure that the carryover component in your laboratory is quite enhanced, so that you don't have an intended transfer of these particular samples. So in quantitative tests, I think I've already discussed this. So the unintended transfer from one sample to another, which can lead to inaccurate results, is particularly important in analyzers. So this one I've already enhanced it or explained it as much as possible. So how do we perform carryover tests in a quantitative environment? There's normally the Ayub harmonized protocol on analytical chemistry. There's always a description on how those particular processes happen, and also there is also CLSI guidelines. So one, testing for carryover is standard part of validating or verifying new instruments and methods. A common procedure involves the following step. So it is a very important component. And remember, our current standard is risk-based approach to our testing. So it is quite important that the testing that we're doing, we are able to look at the risk of harm to the patient as much as possible. And therefore, carryover test is one of the important areas to look at in method verification. So the first step, on the Ayub recommendations of 1991, for example, most of the jurisdictions started doing this many years ago. I think it's now just getting up in our areas. For description and measurement of carryover that affects clinical chemistry, the carryover ratio calculation of the percentage is normally high 3 carryover to low 1 constituting carryover proportion H in the design of 3 high samples and design of 3 low samples, where H you calculate as L1 is always the mean of L2 and L3, and therefore H3 you also minus that and have L1 and L2. Let me explain that. So carryover samples can either be commercially acquired from the various distributors or various manufacturers, or you can also use your own lab-made carryover samples. So whenever you have a very high sample test, it's always important that you retain them for carryover testing for future, so that you don't have to hustle so much when you want to do carryover testing. So very high samples maybe on the higher part of the pyramid. For example, if you are running something like potassium, if you have a sample that is hitting maybe 7 millimoles per liter or 10 and above, or just at the higher analytical measurement range, if you have it in your lab, you need to retain it so that you have very high samples retained for this particular test. And also, you also have to retain very low samples for this particular test as much as possible. So it's normally advisable to have 6 high samples and 6 low samples. So such if you're not able to, minimum, you can always have 3 high samples and 3 low samples. But 6 is normally recommended just to have those repetitive kind of tests. So we are having high lows that are 6 in nature, and sorry, the highs are 6 and the lows are 6. So the study design, so recommended is that you run the first high, you run the second high, and then you run low, first low, second low, third low, and then you repeat with the same sequence as we have already said. So if you are having 6 samples for each, you'll be having high 1, high 2, and then low 1, low 2, low 3, and then high 3, high 4, and then low 4, low 5, and low 6. So you're having only 6 samples in total. You'll just be able to run high 1, high 2, high 3, and then you run low 1, low 2, low 3. So having a total of 12 samples is good because you are able to optimize your testings. And in case there is any false kind of alarm, you are able to have your recovery done quite well when you're having bigger sample components. But you're having smaller, it limits you for that. So it is always recommended is to have a total of 12 samples so that you have those particular designs as per that. So that the second batch is just to ensure that your readings from the previous one is able to be relooked at. So we said we have we prepared the high and low material. I think we already discussed that. And then we load them in the order that we've already planned, as we've already discussed there. So you run your samples as per the routine testing. So ensure that your analyzer, you always run your calibrations, you run your QCs, everything else is fine, just in the normal routine parameters. And then run the samples, the routine testings, and then you record the values that you have gotten in a template, and you need to note any repeats or any flags that are that you're able to observe. So just to visualize that, if you're having only 6 samples, the first high is there. When you run the second high, and then you run the third high, and then you realize that the low one might have the carryover components. You see the red part is the carryover component from a very high value. And then maybe the third one, the second low, the carryover component might be very much minimized. And then the last L3, it's too much minimized. And you proceed like that. So realize that the H1, H2, and H3, there is no major effect because they're already high samples. So even if you have carryovers in these particular areas, they're already high samples enough. And whatever you are transferring might not maybe affect the clinical component of that particular test. But you realize the L3, sorry, the L1, you've already transferred something from H3. So it means that the H portion that is transferred is going to affect that particular test as much as possible. So how do we calculate? We can do the H average of all the H results. And then we'll have our L baseline, which is the mean of unaffected lows. So if we are going back to our previous visuals, you realize that L baseline will be the mean of L2 and L3. So L1 is the first low after the high. So the first low after the high, you can see it there. So how do we do carryover? Carryover is one of the straightforward ways of calculations. You can use an existing template, either from CLSI or ABCD or RICOS or whatever it is, but you can also just do it with your normal Excel template. So we'll be able to minus the values from L1. So the values from L1 that has that carryover component, and then you minus L baseline. So remember our L baseline was L2 plus L3 average. And then you divide by H. So you remember H is our average of the results, of the highs. So H1, H2, H3, average of those results. And then you minus the L baseline. So minus the L baseline, that is L2 and L3. So then you multiply by 100%. So an example case in point. So you have the H average for albumin, for example. In our case here, maybe it's 98.8. So you have your 98.8 there. So our L1, which has carryover component, is about 7. And then our L baseline, which is L2 and L3, has only 2.0 as component. That's just an example. So how will you calculate your carryover? So you'll be able to have L1, that is 7.0, you minus 2.0, you'll be able to get a 5, and then you divide by H, which is the average, that is 98.8.8, and then you minus the baseline, so you'll be able to get a figure like 996.8. So you'll be able to have 5 over 996.8, and then you multiply by 100. And therefore, for this particular test, your carryover is 0.50%. So what is the acceptance criteria? So most manufacturers have always published the acceptance criteria for various tests. So you need to go back to your insert or information for use insert or your machine manual, or if you don't have them there, you need to contact your manufacturer to share with you data on the carryover acceptability criteria for various tests. But this should also be compared with various limits as published by CLSI. I think we are very much fans of CLSI in this part of the world. There's always also the German bit. We also have the RCPA and all those particular things. So it depends with the guidelines that you're using in your lab. But you should also go back to the manufacturer acceptability criteria for various tests. So you remember certain tests should be able to have as minimal as possible carryover percentages as much as possible. So for most clinical chemistry assays, the carryover that is acceptable is normally between 0 to maybe 1%. But for very sensitive analytes like even troponin, a carryovers should be very minimal, very, very minimal. So you'll find 0.1 to maybe 0.5 is acceptable for certain tests. So you need to consult your inserts in that so that you are able, once you calculate your carryover, you either accept or reject whatever you've calculated, and you're able to see that this machine might not be fit for use for certain tests, and therefore it's a very important component if you look at it. So how do you interpret? So if it means the specifications, you need to document the whole of this and then you approve. So remember, in method verification, the raw data and the primary data is quite important, so that when you are doing your verification, you should be able to have traceability component of the data that is out there. So if a test sample fails carryover, you need to verify the sample order. Was your sample order the right way? You need to do a rerun. You need to adjust the washing cycles and use disposable consumables that we said earlier, just to find out if the issues might have arose from those particular areas. If unresolved, you need to escalate to the service provider or vendor just to ask what could have gone wrong. So for qualitative tests is also quite important, especially if you're running the TTIs in the laboratory. You don't want to carry over a test from a negative sample into a positive one, especially if you're going to do transfusion medicine and many others. So maybe you'll be able to tackle carryover test in qualitative test, maybe in one of our webinars. Notes and tips. What is the frequency of doing carryover? Perform at method verification. Perform after major maintenance. Perform it annually. Or if you have a quality assurance plan or a quality management plan, you need to perform it at that particular plan. Remember, now we're moving towards risk-based approach to quality management system. So when you're doing, before you introduce a test in the lab, you need to also do the carryover tests. After an engineer comes to your site and has done major maintenance, and certain components of your testing are quite highly sensitive, you need to at least also do carryover tests for those particular analyzed. Or you should be able to schedule it annually. During the preventive maintenance or major maintenance, you need to do a carryover, or just schedule it annually when you need to do it. Documentation, you need to record the date, the instrument, the assay, the reagent lot, the operator, the raw results, the calculation, acceptable limits, conclusions, and approvals. So this I don't need to re-emphasize a lot because we're already operating in the quality management ecosystem. Notes and tips. You can use pooled samples similar to patient samples. You can use commercially available samples. And for sticky analytes, consider the order of high, 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 and then low, low, low. So if low is 0, use the smallest measurable non-zero value to avoid division of values by 0. So don't use analytes that have 0 components, or don't use blanks, whereby you're using the diluent to use at your low level. No, get sample that is near low as much as possible, so that you avoid issues of dividing numbers by 0. So these are some of the few tips that you need to be aware about. Include raw data and plots. I think we already said that. Acceptability criteria. So attach results to the method verification records. So I think I've already done that. So general recommendation. So when do you need to do your carryover? So when you've introduced a new method, a new instrument, so you need to do that. When there's consistent disparities between EQA and IQCs, you need to look at whether your carryover is an issue. When there's major maintenance or calibration shift, you need to do that. Reagent lot, if you feel that reagent lot will affect that, or you are not, once you do the reagent lot and you're not seeing some of the things, so you need to look at it. Or if the manufacturer himself do a recommendation, you need to also to put that into consideration, because most of the time most lab scientists don't really read what are the recommendations from the manufacturer. So you can also say that every 6 to 12 months, as per your lab policy, as per the risk assessment, you need to look at that as per instructed by the manufacturers. So if you look at CLSI, the EP47 document, you could be able to get how you need to do that. And then if you look at risk-based approach to managing your ISO 15119 protocols in your lab, carryover should form part and parcel of your components. So if you're looking at using a lot of clear guidance document as well, you can be able to get more information there. So best practice carryover testing is typically not repeated or retuned schedule unless changes in the testing system could affect the performance. So you need to see what is the risk-based approach for your testing. So this is just the requirements of the standard. You need to verify for better clinical making or clinical decision-making components. Okay. So I know the current standard has placed a lot of emphasis on the accuracy, precision, and linearity. And as you are a good student of the standard, as things go forward, as things become more strict and stringent, the next revision will be able to have those elements of carryover as well. So remember, this particular process must be performed by competent personnel and documented by verification protocol and report, and includes the review of manufacturer specification, analytical performance, comparison with reference methods, quality control material participation in quality proficiency testing where applicable. So your lab should be able to have those good quality infrastructure as much as possible. So verified method must be documented. We've already discussed that. So I'll not be able to belabor it. So I'll leave it there and maybe just invite Haroun to take us to the marketplace. And then after that, we'll be able to take questions and answers. Thank you. So Haroun?
Okay, so let me, sorry, I had a network issue, so let me unmute.
So as we wait for Haroun, you can type your questions in the chat box. You can prepare that so that we are able to attend to them.
Okay, briefly, I'll be able to share with you some insights or some of the carryover reduction tools that our equipments are able to use. An example, we'll go through the SNIBE biochemistry or the SNIBE Maglumi series. So analyzers that you find that have the reusable cuvettes will be able to be incorporated with multiple wash needles that need to clean the cuvette severally. So for biochemistry, you'll find that you have four needles that one will do the washing using detergent, and then the other two will be able to use distilled water. And another feature that manufacturers will be able to add will be heating element to the liquids, as warm liquid will be more effective to be able to clean those particular cuvettes. So those series of washing will be able to assist that particular process. So as you also interact with the equipment in your lab, you need to check on that particular cycle, or once the engineer or the application specialist is taking you through the equipment, those are some of the key questions you need to ask. And then the other aspect is single-use cuvette for equipments that are able to, and as also Anthony mentioned, the aspect to do with single-use pipettes as well. For equipment that have a single probe, you need to find out how effective the cleaning cycle is. So for snipe equipment, you'll find that the cleaning cycle is done using high pressure jet valves that is able to clean off any remnants to the probes. Find out also the type of material the probe is made with. So you have a Teflon coating that is usually on the probe, and it's also a part of the laboratory's protocol to always check the probe. So you find that after several use, you find that the probe might start flaking off. So if you find the machine came with maybe a probe that was black, and then after a while you find that it has flaked off, you need to be sure that remnant particles of the reagent or the sample are not remaining on the probe. So the aspect that you find the manufacturers are employing or using the Teflon coating is Teflon is a material that is hygroscopic, and it will not allow liquid to stick to it. So if you have a liquid that has been dipped, or the probe has gone into the liquid and it comes out, you find that Teflon will repel that particular molecules of the liquid. So this will also help in point to reduce the carryover aspects of the probe. The other aspect will be the detection techniques that the probe uses. So most of the analyzers, you'll find that they do not get immersed. The probe will not get immersed into the liquid. It's only the tip that is usually sensitive. So once it detects the liquid, it stops and then only enters by a millimeter to pick the appropriate liquid and then gets out. So that has to be taken note, and you find that as well in terms of maintenance procedures. Remember, some of the probes, due to continuous use, you find that it might be entering the reagent. Yes, it will not dip the tip directly into the reagent, but it will be able to scrape off if the alignments are not correct. It will scrape off on the surface of the reagent or the surface of the tube. If you have not correctly have the pipette probe aligned to the wash position or the sample collection position or the reagent positions. So that aspect of us going up and picking up those particular remnants can be a potential risk to carry over. So you find that you are always advised that maybe at the end of the day, you take a swab, alcohol swab, the 70% alcohol swab, and you wipe out down the probe. So despite you doing the deproteinizing effects at the end of the day, you're doing the sample probe cleaning or shutdown procedures, usually the aspect of cleaning off is also recommended using the 70% alcohol as part of daily maintenance for the laboratory. For higher throughput equipment, you'll find that you are using single cuvettes. So if a manufacturer has opted to go with the single cuvettes, you find that they are increasing or reducing their chances of having carryover. And you'll find that in the statistics for carryover tests, so if you go to your user manual, as you look at the precision, accuracy, and linearity studies claims of the manufacturer, you'll also look at the carryover effect. So this is always on all manuals, and it's a part you need to really study well so that you can be able to be sure of that particular percentages are at the minimum or are as per the recommendations of CLSI guidelines. So if you are able to use maybe the single cuvettes and they're getting damped off, that should be very okay. Now, the other aspect that comes in with the auto chemistry analyzers or auto immunoassay analyzers that use maybe cleaning of the cuvettes that are the reusable ones, you'll find that there's an aspect that is called cross-contamination or cross-wash. So SNIB equipment, you'll find that after it has run a series of tests, so assuming, let's say we have 80 cuvettes and I've ordered 10 tests, the 10 tests will occupy maybe test the cuvette number 1 to 10. Now, after it has finished pipetting of these particular samples, you'll find that the probe will go and pick the wash detergents or the wash solutions that are provided as a consumables with them for the equipment, and it will subsequently clean the next 3 cuvettes that have not been used for testing. So you find you have 0.1 to 10 that were used for testing, but then you have 0.11 to 0.13 that are done a cross wash. So this depends with the risk that the manufacturer has given, and usually there is a sheet that the manufacturer gives, and if there is a high risk of cross-contamination between analyte A to B, so let's say AST and ALT, you'll find that the way the probe will dispense those particular samples in the cuvette will be different. So you find that if AST and ALT has a high chance of cross-contamination, you'll find that it will not place those particular tests together. So those are some of the aspects or highlights from equipment experience that you can look into or further read about in the user manual on how that particular manufacturer of that particular equipment is actually able to minimize the cases of carryover. And then as a lab, as you do your method verification, then you need to actually do those actual tests, and you get to confirm or validate the manufacturer's claims. Thank you. So maybe we can go into the Q&A session, Antony. Is that okay?
Yeah, I think we can proceed.
All right. So if you have any further clarity, the mic is unmute. You can be able to raise your hand or unmute and just be able to ask. So on the Q&A, we have Sam from Nairobi, enjoying the learning early in the morning. Nice topic. Thank you, Sam. Collins Mulesha, greetings. Thank you for the great presentations. Does a measurement uncertainty study study design be considered as a carryover percentage, or can the carryover study be used in determining measurement uncertainty? Thank you. Antony?
All right. Thank you for that question, Collins. Carryover testing is majorly measurement characteristics for method verification. So for the purposes of measurement uncertainty, so remember measurement uncertainty is a non-negative parameter attributed to a test. Every test has a true value somewhere, but there are those impediments or those budgets that normally bars from getting the true value of a test. And that therefore, those particular budgets that do not allow us to get a true value of a test is normally attributed to measurement uncertainty. So when you look at measurement uncertainty, you have to come up with what might make your test not really achieve the true value. So things like environment, things like reagents, things like many other things that are measured either through the precision studies and also from accuracy studies and etc. should be able to help you arrive towards measurement and certainty. But carryover has not been designed as one of the components that are going to be used for determination of measurement and certainty. It is just one of the measurement characteristics for method verification, just as accuracy, precision, and linearity. So you realize that most of the laboratories at times use these other measurement characteristics like accuracy and precision data to determine measurement and certainty. But you realize that other components like linearity, like carryover, like robustness, like ruggedness may not be able to be applicable when you're doing your measurement and certainty study design, unless it is those intensive study components that are involving actually coming up with certified reference materials in labs that are of reference in development of these particular components. But from the studies that I've looked at, carryover is not a component when you are designing a measurement uncertainty study design. Thank you. Any other question?
Thank you.
So feel free to unmute and then you can give us a call.
Okay, anyone else with any queries? We can have open discussion. You can be able to also comment or give feedback. Thank you.
All right. So I believe there's no any other further questions, unless Haroun needs anything else.
No, we've handled the Q&A and the chat section. So, okay. And we have no hands raised. So I think that one is in order.
All right. So it's a new topical area for most of the laboratories, and virtually we normally get a lot of questions, especially in topics people are familiar with. So I think as the topic advances, as the lab medicine advances, we are able to also bring you some of the developments in other parts of the world, so that at times when your testing go wrong in the lab, you keep on wondering what are the issues that we have. And most of the time, our go to back default testing or setting for most laboratories or for most lab scientists normally, is it a calibration issue? Is it a QA issue? Is it all these issues? But if you sit down and look at the sources of variations in the lab, there's so many sources of variations in the lab. So carryover is an important area, and I will urge you to look into it, to develop your protocols around it. and just to see how best we can be able to tighten our patient safety and ability to just enhance patient ability to move. So I think if there's no any other question, we will today finish early so that you're able to also to retire to other things. So I'll take the meeting back to Haroun.
Okay. We'd like to thank our presenter, Mr. Antony. Thank you for the great session. We also have a comment from Sam, a great presentation. So thank you all for making time to attend today's webinar. As always, before the end of the week, we'll be able to post your KMLTTB CPD credits to your accounts automatically. Should you have any queries, you can be able to always reach out to us to cpd@ketonconsulting.com. And then we will also be able to issue certificates for today's webinar. So from your email registration, we'll be able to share with you the certificates. Also, on our WhatsApp group, we'll be able to share the webinar recordings should you have a need to be able to refer back, or should you have a need to refer back to the presentation. We'll also be able to share that with you on your emails. We appreciate your attendance and thank you for making time to learn with us as Keton Consulting. We are happy to have you. So, Antony,
Right.
just a few comments on chat.
Sorry?
Maybe Sam is inquiring. Maybe you share to us an article on that topic. We go and do some further studies on it. Seems a bit complicated.
All right. I can see, you guys are just now asking questions. So maybe you share an article on that topic. We go and do further studies on it. Seems a bit complicated. Thank you, Samuel Mayaka. The topic is quite straightforward, and it is just as scientific as many other components. So at times you wonder why a patient is okay. The doctor is telling you the patient is okay, but you are getting the sample as pathological, and you wonder what really has happened. So you need to check the carryover safeguards for your equipment as much as possible in the laboratory, so that you check whether the leftover samples from one patient X, maybe Anna, and patient Y, John, whether they have those cross-contamination that normally happens. So we'll share with you the notes as usual. We'll also share with you the YouTube link for the video. You can go to our YouTube channel and you're able to learn more from it. You're able to do your research from it. And for those who are doing their masters or their PhDs or their bachelors or degrees, it's quite an interesting area that you can also pick up just to study the carryover test in your laboratories, especially maybe the high sensitive tests like troponin, like maybe potassium and their impact on patient safety and all those kind of things. So there's a lot of areas to be able to research about when you're doing your masters or your thesis or your anything else in the laboratory ecosystem. So I'm okay. We can be able to interact and see how we can be able to work together for that, Mr. Samuel. We also have Perez Aoko. How often do you run the high and low sample since we have the IQC? So remember, for carryover, you're looking at extremely high samples, not just pathological. So remember, the IQC samples are majorly either pathological or they are non-pathological samples. So, and most of the time you'll find that for pathological samples, they're not the extremely high levels of pathological samples. If I'm to use a component of HIV viral load, for example, if you get 10 million copies of a sample and then you get maybe 1 million copies of a samples, for carryover testing, it's always good to use the highest level, the 10 million copies of a sample, because anything highly concentrated is what is able to easily have that transfer happen. And also the impact of that transfer of highly concentrated sample is higher compared to the lowly concentrated samples. And therefore, if you went to school during our times, we used to go to school with juices called quencher. So you'll be able to have the quencher very highly concentrated, therefore you need to dilute it. So give yourself an opportunity to see, okay, fine. This highly concentrated media, when you have the next one that is water, it's still able to transfer the high concentration on the other side. So IQC is good. IQC is the first entry point for quality infrastructure. But for carryover samples, the very extremely high and then the very extremely low is what is normally used just to assess your machine's ability to see whether there is minimization as much as possible in the carryover ecosystem. So that is how it happens, Paris. I don't know that there's any other questions that are coming up. It is not a hard topic. It's just a new topic for this part of the world, but it's a topic that has been there in other parts of the world as much as possible. Thank you, Joseph Ombayo. I can see, good idea. Okay. So Haroun, I don't know whether there's any other comments.
No, I think on the Q&A, we have no any other. Also on the chat box, we have exhausted them. So maybe also a comment to Samuel. A good starting point will be from the user manual. Just go through where the manufacturer's claims are. So as usually peruse through the precision, the linearity aspects, the accuracy aspects, check the content on carryover so that you can have further details as well, so that you can really investigate or really question the equipment that you have, so that you can have also more further information. So it's a good starting point, starting with the equipment that you currently own, and then just be able to familiarize yourself with what are those particular percentages that the manufacturer is claiming. And also a good resource point should also be also from the manufacturer. So you can be able to request from your current distributor, or you can even contact the manufacturer directly, and you will be able to get those particular studies or claim. So the manufacturer will write a paper on their carryover studies, and then you can be able to look through what are those aspects that we've discussed. How do they prevent them? How do they omit them? And how do they ensure that they are kept at a minimum? And what are those particular percentages, so that remember, for these particular claims, you usually have a reference point, so that as you're doing your carryover studies at, let's say, for HGB in your hematology analyzer, remember whatever results that you will get, you'll have to refer them to what the manufacturer was claiming, so that as a method verification characteristics or a tool, you'll be able to see that the manufacturer was claiming that the percentage is 0.2, and you got maybe a 0.2, then you say, okay, in affirmation, the two results have been correct between my study and the manufacturer study. So always refer to that particular aspect, and further details can always be obtained from the studies the manufacturer has published, as the one that usually is in the user manual is usually the summarized point or the results of it. So you can have more study review on the paper, where they will have the how the studies was conducted, the original sample results, and the original sample percentages before they did the summary on the user manual. So it's a very good resource point, starting with the manufacturer's claim points as well. Okay, otherwise, thank you so much for attending. I think I hand it over to Antony for closing remarks, and wish you a lovely day ahead.
Thank you very much for attending. I think we'll be tackling even newer topics in the coming few weeks. We are looking at something on the next generation sequencing and the bioinformatics. So I think labs are more towards now precision medicine. So whether it is about oncology kind of panels, whether it's about fertility, whether it is about NIPT. So we are researching as much as possible and see how we can be able to introduce those so that diagnosis of things like cancer can be able to explore the issues of the next generation sequencing, whereby from a simple fluid or liquid biopsy, we are able to really know to the nitty-gritties so that we are able to help patients or doctors diagnose this as much as possible. So we thank you for the support. I think this is our 10th webinar consistently every week. And we hope to tackle more as we move forward because still a lot to be covered. And we want to thank you and wish you a good day. All the best.
Mr. Antony, Samuel Odor, you have your hand raised. You have a burning question or a comment. Please feel free to unmute.
Okay, thank you. Let me lower. Sorry.
Okay. All right. Thank you, guys, for attending. Have a lovely day.
Bye-bye.
Thank you. Bye.